we defined refraction earlier this week as the bending of light. When it goes from one medium to the other, it changes speed. It either slows down or speeds up, depending upon which way it's going through the boundary. As a result of that change of speed, the wavelength changes, but the direction also changes. So if you've got, let's say, a ray of light going from one medium to the other where, let's say the index of refraction of this medium is high, and the index of refraction of this medium is low. In other words, the index of refraction being a measure of how much light bends, being a ratio of the speed of light in a vacuum to the speed of light in that medium. An index of refraction that's high to an index of refraction that's low, this light beam will speed up. It goes faster with a low index of refraction than a high index of refraction. It will speed up. As a result of that increase in speed, the wavelength will increase. As a result of that increase in speed, the angle will also increase, such that theta 1 is smaller than theta 2. If we change this up a little bit, and we say that the first index of refraction is low and the second index of refraction is high, maybe we're going from air to glass here. Right? What's going to happen? Well, the light's going to slow down. So as it's going from the first medium, air, to glass, the light slows down. As a result of that slowing down, the wavelength will also decrease. That wavelength decreasing also causes a change in the direction such that theta 2 ends up being smaller than theta 1. So when you're going from low to high, the ray bends toward the normal line. The angle decreases. When you're going from high to low, the angle increases as a result of the increase in the speed. Does that make sense? Now, yesterday we wrote down on the board an equation that kind of puts all this together. It was Snell's law. Sine theta 1 over sine theta 2 equals V1 over V2, right? As V goes up, theta goes up. It also equals lambda 1 over lambda 2. As lambda goes up, then theta goes up, and V goes up. But it also equals N2 over N1. In other words, as N goes up, theta goes down. They're inversely proportional to each other, right? N2 over N1, theta 1 over theta 2. You can see here, as N went up in this case, N increased. What happened to theta? It decreased because N increased and because the speed decreased as a result of that. Whenever you're solving problems using this equation, you got to pick two parts. There's 4 parts here. Pick 2 parts, set them equal to each other. Okay, solve for what you're looking for. Today we're going to talk about something that's kind of an extension of refraction. We're going to call it total internal reflection. Sometimes we abbreviate it as TIR. You guys already have the notes photocopied for you there, I think, for this. Total internal reflection. This is a phenomenon whereby a ray of light, when it's going from one medium to the other, doesn't always refract. It doesn't always keep going and change direction as a result of the change in speed, but rather sometimes it will reflect. But it's not a random process. It doesn't reflect at a random time whenever it wants to do it. It reflects as opposed to refracting in very specific circumstances. I'm going to draw you another picture here. And we'll get to the point where this light ray reflects. The first medium is going to be a low index of refraction. Maybe it's going to be air. Okay, 1.00. The second medium is going to be a high index of refraction. Maybe it's going to be glass, which has an index of refraction of about 1.5, give or take a little bit. You got a ray of light with a certain theta 1 there that's striking that boundary. That ray of light will refract. It's going to speed up or slow down. What's going to happen to it? Speed up or slow down? We're going from low to high index refraction. Yep, it's going to slow down. If it slows down, then theta is going to get smaller, right? Theta 2 will be smaller than theta 1, right? Let's increase the angle of incidence a little bit. That's an angle of incidence that's about twice as big as my original angle of incidence. What's going to happen here? It's still going to slow down, right? That's still going to make theta smaller. Increase it even more. Now we got a massive angle of incidence here. It's almost 90 degrees. Light's still going to slow down. It's still going to bend toward the normal line. Now you're going to find that the angle of refraction is bigger than it was in the other two cases, but it's always still going to be smaller than the angle of incidence. So going from low to high index of refraction, light slows down, the angle will always decrease, and you're always going to end up with a theta 2 that's smaller than theta 1 in every single case when you're going from low to high index of refraction. But let's change this up a little bit. Now, instead of going from low to high index of refraction, let's go from high to low. So this time we're going from glass to air, or something like that. Index of refraction of about 1.5-ish to an index of refraction of about 1.0. This time we've got a ray of light striking that boundary at a pretty small angle. What's going to happen to it? Speed up or slow down? Speed up. Yeah. As a result of speeding up, the angle is also going to increase. So instead of bending toward the normal line, it's going to bend away from the normal line like this. We're going to find in this case that theta 1 is less than theta 2. So instead of the angle decreasing, the angle is going to increase. Let's draw another ray of light. Here our angle of incidence is about twice what it was before. That's going to cause an even bigger angle of refraction. Still see that theta 1 is bigger than theta 2, and theta 2 is bigger than it was the last time, because our theta 1 was bigger than it was the last time. Let's increase it even more. See what happens. This time, our angle of incidence is about 3 times what it was the first time. It doesn't really matter if it's 3 times or 2.5 times or whatever. It's bigger than it was the last 2 times. The angle of refraction is going to increase even more. Well, there comes a point when that refracted ray doesn't really refract. Rather, it kind of just skips along the boundary there. It kind of just goes right along the boundary between the two materials, the one with the low index of refraction and the one with the high index of refraction. Okay, that's something different, because that's not really refraction, is it? It's not really going into the new medium. Watch what happens with the next one. Now we're above that red angle, that red theta 1. What happens to this light ray? It doesn't refract at all. It doesn't even skip along the boundary. Rather, this ray bounces up. It reflects. It's kind of like skipping rocks in water, kind of. The analogy falls apart at a certain place. We'll see if you guys can figure out where the analogy falls apart. Okay? When you throw a rock, you're standing by the pond here, and you throw the rock straight down, almost straight down into the water. That rock goes into the water, right? It's going to change speed, and it's going to change direction as a result of going into the water. It will. If you could measure the direction of that rock through the water, you could see it clearly, then you'd see that it would change direction. What if I increase my angle of incidence a little bit more? Well, it's still going to go into the water. It's going to change speed. It's going to change direction even more, but it's still going to go into the water. Increase it even more, more, until I do it like this. What happens to the rock now? It bounces off. If you increase the angle of incidence to a point that's greater than a certain angle that we're going to call the critical angle, then you're going to find that this light ray is going to reflect as opposed to refract. Where does that analogy fall apart? James? Sorry? Okay, shape of the rock could affect it. Absolutely. No, absolutely it could. Okay? Light doesn't have a shape, so you're not going to run into that complication. Absolutely. It's not what I was thinking of, but it's a good point. At no point would the rock just go along the surface? Yeah, probably not, yeah. Although in practice, you don't really see that with light either. There's a theoretical point that it would, but it's hard to actually observe that. Okay, the rock comes down after it's bounced because you got gravity in there. Yeah. Again, not what I was thinking of, but Yep. It is actually when it bounces off, the angle of incidence would equal the angle of reflection, but that would be the case. That would be the case with this black line as well. Okay, if it strikes it at 80 degrees and it reflects, it's going to bounce off at 80 degrees. That's true. Yeah, yeah, that's a good point. We don't have that complication with light, right? Because light always travels at the same speed, right? Well, that's not true. In different media, it travels at different speeds, but not going to have that complication. Yeah. Yes, that's what I was looking for right there. The media are switched, right? Here, for real total internal reflection to happen, for the real deal, it's got to be from high to low. You can't get it happening from low to high. But when you're skipping rocks, where are you going? From air to water, not from water to air, right? So the mediums are switched there. This was an analogy. This is not total internal reflection, but you can see how increasing the angle, you can see at some level how it can cause reflection to take place by that analogy. Okay? Total internal reflection has to happen. If it's going to happen, when you're going from a high to a low index refraction, as opposed to a low to a high index refraction. Let's define total internal reflection. Let's define critical angle. And then we're going to show you a couple pictures and give you some applications of total internal reflection. We're going to say total internal reflection is the phenomenon. That's a big word, eh? The phenomenon, if I spelled it right, whereby a ray of light going from a high index medium to a low index medium will reflect instead of refract. In other words, a ray of light goes from glass to air, from diamond to air, from water to air, from glass to water. Maybe it doesn't refract. It still can, depending upon the angle of incidence. But it doesn't always. Okay, it can reflect. But remember, it has to be going from high to low index of refraction, never the other way around from low to high. What's the critical angle? Well, it's the minimum angle of incidence at which total internal reflection begins to occur. That's that point where the light would skip along the boundary, not really reflect or not really refract. It's kind of in between. It skips along the boundary. Anything above that angle, reflection is going to take place where the angle of incidence will equal the angle of reflection. Anything below that angle, it's going to refract as normal. The minimum angle at which total internal reflection will begin to occur. Let's flip the page. You guys have got the picture of this pond on your notes that I copied for you here yesterday. We're going to add something to this pond. Question? Yep. We're going to add a fish to this pond. Okay? It's not just a pond with a couple plants growing in it. There's a fish in the bottom of the pond. He's a big fish. He's a happy fish. And he's got a red outline with blue skin or blue scales. You got a guy standing over here on the ground. He's just enjoying the day, looking up at the sky, okay, looking at the pond, and all of a sudden he sees this fish. Hey, there's a fish in there. Why does he see this fish? Well, the fish doesn't generate any light of its own. The fish has to reflect light, and the light ultimately comes from the sun. There's millions of rays of light coming in and striking this fish, reflecting off at all kinds of crazy different angles. Let's pick one of them. One ray of light that reflects off of this fish, right there, strikes the boundary between the water and the air. By the way, the water has an index of refraction of about 1.33, and the air is about 1.00, about. What's going to happen to the speed of this light ray that originally came from way up in the sky but came down into the water, reflected off of the fish? What's going to happen to the speed of it? Is it going to decrease or is it going to increase? Somebody said it? It's going to increase, Stephen, right? Because it's going from a high to a low index of refraction. If the speed increases, then the angle will also increase. So this ray of light that had a certain angle of incidence, theta 1, that looked like that, is now going to have an angle of refraction that's bigger. It's going to look like that. Right? Theta 2 is bigger than theta 1. Why? Because V2 is bigger than V1. Why is that the case? Because N2 is smaller than N1. This guy's going to see the fish. But he's not going to see the fish where he thinks it really is. He is going to see the fish where he thinks it is. He's not going to see the fish where it really is. He's tricked. The fish has tricked him. It's not really the fish has tricked him. It's his own mind that's tricked him. His mind thinks that that light ray that went into his eye never changed direction. His mind thinks that it always traveled in a straight line. So in other words, if we extrapolate this back, the guy is going to see the fish back here. He's going to see the fish just as it is, except it's going to be not as deep as it really is, and it's going to be behind where it really is. You ever notice if you go golfing and you hit the ball in the water, and you take your golf ball retriever and you try to get it, it takes a little bit of fishing around because you see the ball somewhere, but then when you go to put the retriever there, the ball's not there. The ball's somewhere other than where it really appears to be. Okay, it's because your mind is tricked into thinking the ball is in a certain place because the light, although it bends when it goes from the water to the air, your mind doesn't recognize that. Your mind sees it as having always traveled in a straight line. So the fish appears to be not as deep as it is and behind where it is. Does that make sense? This has nothing to do with total internal reflection yet, right? This is just refraction. Let's take this guy and put him back a little bit. He backed up. Said, I want to see this pond from a different angle. Okay, I want to see this cloud from a different angle. Well, this light ray that reflected off of the fish, it's still reflecting off of the fish, but now it sails right over his head. He doesn't see the fish in the same place anymore because that light ray that he extended in his mind back here, not getting extended in his mind anymore because he doesn't see it. But there's more light rays. Okay, we picked one ray reflecting off of the fish. There's many, many more. So let's take another one. Let's take this one. That's got a bigger angle of incidence than we had last time, right? Okay, that might cause a bigger angle of refraction. This might sail into his eye right here. He's going to see the fish in a different place again. But what if theta 1 is now bigger than theta c? What's going to happen? This light ray isn't going to sail into his eyes. This light ray is going to reflect off of the surface, or off of the boundary, I should say. So in other words, instead of refraction taking place, total internal reflection will take place. What does this guy see right now? Where does he see the fish right now? Yep, he doesn't. Fish is gone. He sees right now the top of the pond. You ever notice that? You're standing right beside a pond, you can look down and you can see the rocks and the ground at the bottom of the pond, but you back up a little bit and you can't. You can only see the surface of the pond. That's why. Because you're increasing the angle of incidence of the light we're required to go through to the point where it's bigger than the critical angle. So the light reflects off of the surface of the pond slash air. Can't see it. Light never leaves the water. There's still light rays leaving the water, but not the ones that go into your eyes. Where would this guy have to be in order to see this fish this time? He could see it, but it would be kind of awkward. Where would he have to be? He'd have to be in the water. If he was in the water, where would he see the fish? up here floating in the sky. He really wouldn't see it floating in the sky. He would see it above him. But in addition to the image of the fish being up there, he would also see the image of the water up there, and the image of the bottom of the pond up there, and so on. So it would look normal to him, except that he'd be looking up to see it as opposed to down to see it. Now, he could turn his head and look straight down at the fish too and see the fish down below him, but he could see it above him as well. You can imagine, anybody have diver here? Anybody gone diving? Scuba diving? Yeah. You ever notice that you can see under, like, what's below you, above you? Okay, that's total internal reflection. I've never gone diving, but I can imagine how, especially with the buoyant force of the water, and essentially when you're diving, you want to be neutrally buoyant, right? So essentially you're canceling gravity. I can imagine how you could get, that I'm sure that they talk about this in your training as well, but I can imagine how it would be difficult sometimes to tell which way's up. Okay? Because you're looking up and you see the bottom of the pond. You're looking down, you see the bottom of the pond. And you can't tell which way's up or down based on gravity because of the buoyant force. So, how do you tell? And at some point the angle is going to change so that you can see, so you're not seeing the bottom of the pond up at the top anymore, I guess. If it doesn't change, I guess you got to change direction, I suppose. Yeah. Yes. Yeah. Yes, no, that's a good point, actually. If you look straight up, you would get past that. What you see is actually, if you look straight up, and I don't know if you've ever observed this before, you can even sometimes observe this in a deep pool. Try it in the rec center pool. I'm not sure if it's deep enough to, is it? Um, what you can what you can see in a deep enough pool is the reflection taking place. If you're looking straight up, you can see the reflection off to the side, but then there's a ring right above you that there's no reflection taking place, because that would be where the angle is small enough that total internal reflection wouldn't happen. But off to the sides, it's big enough where it would happen. So I guess that's another way you could tell us, like literally look straight up or straight down, and where you see the ring is, yeah, you see the ring is up. Here's another one. 16 years ago, I went and bought a diamond for my wife to be at a place called Spence Diamonds in Calgary. You guys know where this place is, right? Because you hear the ads on the radio. That guy sold me my diamond. At least I'm pretty sure it was. It's a pretty recognizable voice, so I'm pretty sure it was the same guy. When I walked in there, great place actually. Okay, I'd highly recommend it. Great place. You walk in there, this guy takes me into his office, looking around at all these things. Guy takes me into his office and explains things to me. Okay? He says, when you're buying a diamond, there's 4 C's that you got to be conscious of. 4 C's. In no particular order. One of them's color. In other words, usually you don't want any color in your diamond. If it's kind of yellowish, like it's not a very nice diamond. He says it can be valuable if it's like really deep colors because it's so rare, but normally you don't want any color. So that's the first C. The second C would be the clarity. You want it to be clear. You want to be able to see through it. You don't want it to be kind of foggy, right? It doesn't sparkle very much if it's foggy, right? Third C, the carats, how big it is. The bigger the diamond, obviously, the more valuable it is, right? The fourth C, and this is where the physics comes into play, is the cut. The diamond has to be cut in a very specific way, at very clear, specific, exact angles. And what this guy said is that depending on where you go, it may not be cut all that well. You might not see it, okay, right off the top, okay, but you got to be careful because it may not be cut properly. And if it's not cut properly, it's not going to sparkle that much. Then he asked me what I did, explained this to me, and asked me what I did for a living, and I told him, and the look on his face actually at first was kind of priceless because it's almost like, uh-oh, I hope I didn't make a mistake. He didn't, by the way. He was bang on his on the physics of the optics of this. Having said that, when I went in there, it never even occurred to me about the cut of the diamond until he mentioned that to me, right? This is a cross section of a diamond. It doesn't matter what the shape of the diamond is from top. This is what it's going to look like from the side. Okay, oval, circle, square, it doesn't matter. Okay, this is what it's going to look like from the side. Okay, don't worry about the exact angles there and percentages, and don't worry about that at all. Light normally comes into the diamond from the top. Not always, but normally from the top. When it goes straight in like this, it's going to slow down dramatically. Diamond has an index of refraction of about 2.42, and air has an index of refraction of about 1.00. It's going to slow down a lot to 1 point something times 10 to the 8 meters per second. But it's not going to change direction because it's going straight in there. But then it's going to strike the boundary between the between the diamond and the air. That theta 1 doesn't look very big. But because diamond has such a high index of refraction, it's actually got a very low critical angle, which means it's easy to exceed the critical angle. If you were dealing with glass, the critical angle would be higher, which would be harder to exceed. Because this is diamond, and because the critical angle is so low, this ray of light actually bounces off of that surface, bounces over here, such that theta 1 is equal to theta 2. When it gets over to the other side, we'll call this one theta 3. What happens? Same deal. It bounces off of this back up here. Theta 3 would be equal to theta 4 there. Every time a reflection takes place within that diamond, what do you see? You observe that. You observe it. Every time a reflection takes place, you see, hold on guys, you see a little sparkle. Okay? It sparkles. If this wasn't diamond, if this had a much lower index of refraction, it would have a higher critical angle, then we might get the light going out like this. No sparkle. Maybe we get one sparkle, maybe we get one reflection, but not out the other side. Okay? So we get one sparkle instead of two sparkles. Hold on one second here. Okay, almost done. If the cut of it is wrong, this is highly exaggerated here, right? Highly exaggerated. But let's say that the diamond looked like this. The ray of light comes in here. Look, massive angle, way bigger than the critical angle. We get a sparkle there because it reflects off. But look what happens when it gets to the other side. It refracts. So the cut of this is wrong. We get a sparkle, which is better than nothing. But on the last one that was cut better, we got two sparkles for every ray of light instead of one. So the better the cut, the more it's going to sparkle. Make sense? Okay. Monday we'll talk about how to calculate what that critical angle is. Have a good weekend, guys.